All right, let's get into it. Today, we're talking about a really brilliant piece of old school electrical engineering, the star delta starter. And it's all about solving one very big, very powerful problem. So, here's the big question. How do you fire up a truly massive industrial motor, the kind that runs factories or giant water pumps, without sucking so much power from the grid that the lights dim for everyone? It's a huge challenge, but the answer, as you'll see, is surprisingly clever. First things first, we've got to get a real handle on the core issue here. It all comes down to what happens in those first few critical seconds when a big motor roars to life. See, when you flip the switch on a motor like this, it doesn't just gently wake up. It demands this enormous surge of electricity. We call it an inrush current that can be way, way higher than what it needs to just run normally. This puts a ton of stress on the motor itself, and it can seriously strain the entire electrical grid it's hooked up to. And this is where our hero, the star delta starter, enters the scene. It's really just a beautifully simple method that gives the motor a kind of split personality. It starts up in a gentle, low-power mode, and then, only when it's ready, it switches over to full throttle for the main job. So, to really understand how it pulls this off, you need to know about the two different ways a motor's internal wires, its windings, can be connected. Think of it like the motor having two different gears. First up, you've got the star connection, sometimes called a Y connection. In this mode, the three windings inside the motor all meet at one single common point. Now, the key thing to know is that this setup cuts the voltage each winding sees down to about 58% of the full power line voltage. This is our low-power, gentle startup gear. And then you have its alter ego, the delta connection. Here, the windings are connected end to end, making a closed triangle, like the Greek letter delta. This setup gives each and every winding the full 100% line voltage. This is our high-power, full-speed running gear. So let's put these two side by side, because this makes it super clear. When you're in star for starting, you get less voltage. That drop in voltage slashes the starting current all the way down to about 1/3 of what it would normally be. Perfect for a safe, easy startup. Then, once you're moving, you switch to delta for running, and you get the full voltage and full current for maximum power. So the real magic here is how the starter uses these two gears in a perfectly timed sequence. It's basically a little three-step electrical dance. It all happens pretty quick. Step 1 is the start phase. The motor kicks on in its star configuration, starting gently and sipping that reduced current. Then, for step 2, a simple timer just waits, maybe 5 or 10 seconds, until the motor is spinning at about 80% of its top speed. Finally, step 3. The run phase. That timer triggers a switch. The star connection pops open, the delta connection slams shut, and the motor is now running at full power. Okay, but this is where the story gets really, really fascinating, and honestly a bit counterintuitive. We figured out how to manage the current, but what about the motor's actual turning force, its torque? I mean, you'd think, right? It just makes logical sense. If we slash the starting current down to 1/3, then the starting muscle, the torque, should also be 1/3. Seems pretty straightforward.
Yeah? No, that's not what happens. Not even close.
And here's the mind bender. The reason is that torque isn't directly proportional to the current. It's proportional to the square of the current. So think about that. When you reduce the current by a factor of 3, the torque drops by a factor of 9. You only get about 11% of the motor's full starting muscle. It's a massive drop. So why this huge penalty? Well, it comes down to the fundamental physics of how a motor actually works. Torque, that turning force, is created by the interaction of two different magnetic fields, one in the stationary part of the motor and one in the rotating part. The best way to think about it is as a double hit of weakness. So cutting the current makes the first magnetic field 3 times weaker. That's hit number 1. But because the second magnetic field is created by the first one, it also becomes 3 times weaker. That's hit number 2. And since the final torque is these two fields working together, you have to multiply their weaknesses. 3 times weaker multiplied by 3 times weaker equals 9 times less starting torque. So what does this actually mean in the real world? Well, this massive reduction in torque has a huge implication. It means a star delta starter is a very specialized tool. It's not a one-size-fits-all solution. it is absolutely perfect for things that don't need a lot of muscle to get going. Think about fans or pumps or maybe a conveyor belt that starts up completely empty. But it is absolutely the wrong tool for anything that's heavy from the get-go, like a giant rock crusher or a conveyor belt that's already fully loaded. With only a ninth of its starting power, the motor would probably just hum and stall out. And really, that's the whole story. The Star Delta Starter is just this beautiful testament to simple, effective engineering. This idea is over a century old, but it's still used all over the world. It kind of makes you wonder, doesn't it? What other elegant, ancient hacks like this are out there, just quietly powering our modern world, hidden in plain sight?